Good morning, everyone. My name is Amin Minena. I am the Coordinator of Technical Programs and Research at Good Roads. I'll be your moderator for today's webinar. Just a quick housekeeping items before we start. We encourage you all to ask questions when you think of them throughout the webinar through the Q&A function. You can find that at the toolbar on the bottom or on the top of your screen. The questions will be answered at the end of the webinar. And this webinar is being recorded and we'll make it available on our YouTube channel, on Good Roads YouTube channel. So today's webinar is Stormwater Underground Detention and Recharge with Corrugated Steel Pipes. Our co-presenters is our Ray Wilcock, the Executive Director of the CSPI, and Matthew Luzzi, Regional Engineer with Armtech. Without taking too much of from their time, I know they have quite a handful program for you. I'll turn it over to Ray.
Thank you, Amin.
Thank you.
Just to make sure everything's okay, Amin, would you let me know if you can see my screen?
Yes, perfect.
Okay, well, thank you very much, and thank you all for attending today. As Amin mentioned, we're going to talk about stormwater underground detention and recharge, and I am pleased to welcome Matthew Luzzi from Armtech. So what I would like to cover is just a little bit on the Corrugated Steel Pipe Institute, the CSPI, talk a little bit about urbanization impact, the standards, profiles, and coatings and durability of corrugated steel pipe, applications and categories, and then I will turn the presentation over to Matthew, who will cover a design overview, installation, benefits, projects, and then I'll finish off with sustainability and talk a little bit about our carbon footprint. The Corrugated Steel Pipe Institute is an association that represents the manufacturers of corrugated steel pipe and structural plate corrugated steel. Armtech and Atlantic Industries are nationwide players. They have plants pretty well right across the country, from Newfoundland to British Columbia. Hubcap and Frontier are regional players in Ontario and Alberta. We also represent some of the largest steel producers in the world, like ArcelorMittal, they have over 55 to 60 plants worldwide. You may know them as Dofasco out of Hamilton. Ironside, they make machines to produce corrugated steel pipe out of Chilliwack, BC. Leland Industries is in just outside of Toronto in Scarborough. They produce nuts and bolts for structural plate. Advanced Coil Industries produce the polymer laminated coil. Cleveland Cliffs out of Ohio, they make aluminized steel, and Warner Custom Coatings out of Guelph, they produce polymer for structural plate. We also have members nationwide and international, like for instance, 2BIO, which is in France, Rondell and CMP are in Australia, Viacon is in Poland, Marmac is, and Valgroup are down in the US, and Birkenhoek is in the Netherlands. And the reason why they are members of Corrugated Steel Pipe is they rely on us for a lot of the research we do, the guidelines, the standards, and so forth. So let's get into stormwater management and the effects of urbanization, and why do we even need it? Obviously, from a quantitative standpoint, there's increased peak flow rates, increased runoff volume. From a qualitative standpoint, the water quality impacts from stormwater. This is a picture of Highway 400 and Rutherford Road in Vaughan, Ontario, which is just north of Toronto on the way up to the Muskokas off the 400. And if you look at that picture in 1983 versus 2012, there's quite a difference. And I can only imagine what it's like in 2022. 1983, you had a lot of farmland. You had, yes, you did have a highway and some secondary roads, but most of it was agricultural land. And then you look over in 2012 and you can see so much more development that has taken place from a commercial standpoint, from a residential standpoint, huge. So obviously the storms that would hit in 83 versus 2012 are going to be treated quite differently. particularly when you have concrete and asphalt and water falling off of roofs and so forth. Quite different from a stormwater management type system that you would need. You know, when it comes to the major storms that we do have, sometimes it becomes a liability. We just need to get rid of it. And sometimes it becomes an asset, and we might need it for vegetation growth, drought reduction. We might just want to slow it down. This is a picture of a hydrograph, and it illustrates the differences between pre-development and post-development when you do have those major storms. On the x-axis, you have time, and on the y-axis, you have the discharge of water. If you look at that red curve, that is in pre-development. So yes, the major storm hits, it starts to build up, and then it hits a peak, and then it starts to dissipate over time. But in a post-development, when you don't have the trees and the rivers and the ground to absorb that those major storms, and it's hitting concrete and pavement and asphalt and roofs and so forth, you're going to have to do something about that. So the idea is when the system is being designed, you want to design that blue line to more resemble that red line in a pre-development. So the traditional approach sometimes is just get rid of it, get it off into a stream somewhere as quickly as possible and take it away. Nature's way is slow it down. You might just want to slow it down like it was, say, in the pre-development area. So you might want to do something underground. We all know what an outdoor storage pond is, or a wet retention pond. They're in basically all of the suburbs you will find where storm sewers are being funneled out into these ponds and so forth. And they serve the purpose, particularly in suburbia, rural areas. However, they could become a liability, a safety concern. They do take up a valuable property that could maybe be used in another way. Sometimes an eyesore, particularly in those late summer months when, you know, the eutrophication starts and the water turns green, and you know, all kinds of things can happen. And they might require frequent maintenance. Or we could do something like this, particularly in the urban areas, something underground that's going to capture that water and move it off in a much slower pace. The material codes that we use are CSAG 401, and that is the standard that takes care of corrugated steel pipe and structural plate. It is being renewed right now. We expect to have a new edition come out in 2022. And we also use the ASTM standards, the American material standards also. The corrugation profiles for corrugated steel pipe, there are 6 of them. The smallest one starts at 38 by 6.5, and the largest 125 by 25. So we're talking 125 millimeters crest to crest, and then 25 millimeters crest to valley. The one in the middle here, spiral rib, is a smooth wall pipe with ribbed on the outside, and the Manning's flow is about 0.012 for spiral rib pipe, whereas the other corrugations have a much higher Manning's flow, obviously because of the corrugations in the inverts and so forth. However, that is very, very important, particularly with stormwater management, because you might want to slow down that water in those areas when those major storms hit. With regards to coatings, there are 4 of them: galvanized, aluminized, galvalume, and polymer laminated. And this chart shows the different characteristics for coating, design thicknesses, the pH levels, resistivity, ohm centimeter, and the chlorides, which would basically be road salts and so forth. As you move up the scale, you go from galvanized all the way up to polymer, which will perform in basically brackish water, which is a combination of sea and fresh water, and in all levels of chlorides and so forth. So very high salt content, polymer would be the choice of material in those particular areas. We have performance guidelines on our website, in tech bulletins, and also charts. I do a lot of water testing and soil testing, and we're able to look at different sites, particularly across Canada, as to what materials will perform in each particular province or territory or region and so forth. The types of underground detention: you can have pure detention, you can have groundwater recharge, infiltration, where you perforate the bottoms to allow it to percolate out down below. Reuse, we might want to reuse that in some shape or form, maybe in drought reduction or watering fields, or a combination of both. The applications that you might find CSP stormwater detention systems would be high land values in limited space, like parking lots, narrow right of ways, very porous soils, system retrofit, and typically up to 15 hectare sites. So just to recap, with stormwater management, we're talking detention, retention, and groundwater recharge. And with that, I'm going to stop sharing and turn it over to Matthew.
Thank you very much, Ray. Just want to make sure that everyone can see my screen properly. So if Eamon or Ray, you could confirm.
Yep,
Okay.
I can see it perfectly. Thank you.
Okay, so thank you to all who attended and joined the webinar this morning. Today, my talk will focus solely on the use of CSP in stormwater. So first, I'll go over the design codes and the standards associated with CSP and its installation. And then I'll go over how to cost-effectively design CSP stormwater systems, as well as some of the crucial design elements that need to be recognized during this design process. And then I'll get into a few project examples to give some real-world context of how these systems are applied. And then we'll discuss the benefits of using CSP in this way. So firstly, the design codes for less than 3 meter span corrugated steel pipes, determining wall thicknesses, heights of cover, and installation methods will be covered under the OPSS, AASHTO, and AREMA standards for different applications, whether it be highway or railway. The AASHTO method specifically will calculate the minimum cover height for CSP using a standard factor of safety, which works well for small span pipes. But for larger span pipes, say larger than 3 meters, the Canadian Highway Bridge Design Code really compares the span and the rise to take into account that negative arching factor. And it provides a more thorough approach to design based on ultimate strength. And it better addresses deep corrugation structures, as well as the interactions with the soil and considerations for constructability as well. So these methods and guidelines can be found in the Canadian Highway Bridge Design Code itself, or in the CSPI handbook for your reference as well. A simple way to imagine these interactions that I was just mentioning is to look at a cross-section of a pipe installed underground. So a corrugated steel pipe is a flexible, thin-walled pipe that really relies on the pressure of the backfill around it to achieve that ring compression, and ultimately the strength required to handle the loads that are being applied to it. So therefore, it's just as important to have a well-graded, granular backfill with known properties than it is to have a properly manufactured corrugated steel pipe. And through those interactions and using all those design methods and scientific principles, minimum and maximum heights of covers for various diameters and wall thicknesses can be established. And this is, you can reference them in the tables for each corrugation. This one is for 68 by 13. And then you have a table that's also for the other corrugations, for example, 5 by 1, as Ray was mentioning before, 125 millimeter crest to crest with a 25 millimeter drop. Another thing Ray touched on was the different coatings. In Canada, there are many different soil types. So in this map of Canada, we can see that there are different soil conditions in different locations, and these will present different challenges and affect steel differently. So for whatever soil type we find in Canada, whether it be pH, low pH levels, elevated chlorides, sulfate levels, low calcium carbonate levels, Either polymer laminated, aluminized, or galvanized coatings will be able to withstand those environmental challenges, and in most cases achieve the desired design life that is associated with that project. So now let's get into how to cost effectively design and lay out CSP for stormwater management systems specifically. So there are three main goals that you really need to have in mind, which are reducing the footprint of your system, eliminating any unnecessary welds within the system during its fabrication, and then looking at ways that you can reduce unnecessary structures within the full site servicing plan by incorporating those components within your steel system. So I'll go into depth on those three different categories now. So first, reducing the footprint. The goal of any CSP stormwater management system should really be to maximize that vertical space available to minimize the overall footprint and thereby reducing the amount of material, excavation, and backfill costs associated with the project. And to do this, we want to use the largest diameter possible. We want to take advantage of CSP's ability to go up to a very large diameter pipe. So if you consider comparing a 1200 millimeter diameter pipe versus a 2400 millimeter diameter pipe, you can see when the diameter is actually doubled, the usable volume is actually increased by a factor of 4. So that's a really powerful tool to use when designing CSP stormwater management systems. So if you consider these two systems, increasing the depth of the CSP detention system will allow for a smaller footprint while storing the same amount of water. So system 2 on the right, made from a smaller diameter pipe, a 900 millimeter diameter pipe that provides around 141 cubic meters of storage. Now system 1 on the left is made from 1500 millimeter diameter pipe that provides essentially the same storage. However, system 1 is the most economical design as it reduced material fabrication, excavation, backfill costs. Having fewer runs of pipe will cut down the number of welds, special fabrication requirements. Having fewer welds will also cut down on lead times from manufacturer. In addition, system 1 just has a smaller footprint at 120 square meters smaller than system 2, which really allows for more space for other underground infrastructure. And really the only way that system 1 may not be the best option is that if you don't have the available vertical space for depth of burial. So if you have that vertical space to take advantage of, you really should increase that diameter of pipe to increase that volume efficiency. The second thing to consider is eliminating unnecessary welding. So the rule of thumb here is to use as much straight pipe as possible to reduce the number of T's and elbows in the design. So doing so will result, of course, in a more cost-effective and efficient design and will ultimately reduce lead times in manufacturing. So in this example, both systems are designed with, say, an 1800 millimeter diameter pipe to have roughly the same amount of storage. However, system 2 uses only 2 elbows and 1 T, whereas system 1 uses 4 elbows and 6 T's. So you can see how that each system can be optimized to really take into account that manufacturing process. The last thing to consider when talking about just the layout and the overall design of these systems is, costs can also be reduced by eliminating, some other maybe concrete structures such as catch basins or outlet control structures by incorporating them into your CSP system. So if you can imagine an inlet structure and a riser with a graded inlet can be added to a system at maybe the low point of a parking lot to eliminate maybe a concrete catch basin that would have been incorporated into that full site servicing design, you can incorporate it into the steel system. You can also incorporate manholes and access risers. There's no need to use any other materials, just incorporate it right into that main barrel. You have a nice access ladder for maintenance purposes as well. Also, internal weir plates and multiple external outlet stubs often can be used to eliminate, separate outlet control structures that are downstream. And you can also use inlet header or manifolds and just make them right out of CSP. The flexibility in the design of CSP really is limitless in these applications. So this custom fabrication really allows engineers to be creative and design customized systems to meet their site-specific conditions, which will benefit clients in terms of functionality and reduce costs. So in this picture, you see a flow regulator. You can build that right into the CSP pipe, so you can really control the flow of that stormwater that's being contained in the system at a regulated rate. Just as Ray was saying, you want to slow down that release of water so you can control it through these flow regulators. Ray also touched on that CSP can be used for infiltration. So CSP can be perforated and to allow for that infiltration when considering a retention system. So those perforations will really allow for that recharge back into the groundwater. And of course, you can remain solid wall as well if you wanted to go for a detention system. It really is a flexible material to be using. Some crucial design elements to really be aware of when designing these CSP systems, some things to look out for. First is that overlapping welds should never be done. So for example, risers shouldn't be located in the middle of an elbow. So this would result in an overlapping weld, which really weakens the structure when you're looking from a manufacturing standpoint. So risers are generally best offset and are best placed on the barrel as opposed to the header. Next thing to consider is the proper spacing of the runs of pipes. So the proper pipe spacing allows for a backfill and is crucial in the performance of these CSP detention systems. So it's important to allow the contractor installing the system to get in between the pipes and work that backfill material for proper compaction. So we were talking about before, that soil steel interaction really is what causes that strength of the system. So we really want to be able to facilitate that proper installation. Next, CSP detention systems really can't support many dead loads from buildings or other structures. So the risks and designs must be analyzed for those on project-specific basis. So building under structures is really something that you have to take into account, and it's not something that we often recommend. The last thing is buoyancy. So whenever the water table is above the invert of a pipe, the potential for flotation really does exist. So that should be accounted for the design as well. As with any of these stormwater management systems, buoyancy is really something that needs to be taken into account. Okay, so we've looked at some of the design considerations, how CSP can be flexible and what to do and what not to do. Now I'll take you through an example that was done in British Columbia. So this project was for an employee parking lot at a Vancouver International Airport located in Richmond, British Columbia. So the YVR is a world-class airport, and they were adding a 460,000 square foot designer brand retail outlet with over 200 shops, really big facility. So they really needed to move their employee parking lot to another location located on the North Service Road with the access to the airport. So this meant that they needed to account for the stormwater management of that parking lot. So the design constraints for this project was the system volume needed to be 200 cubic meters. They needed to contain that stormwater to maintain the natural pre-development groundwater flow. So they had to fit that system within a trench with a width of 4.8 meters and a maximum depth of 1.9 meters. And they wanted to achieve a minimum of 75-year design service life. So how do we tackle that design using CSP? So the first step was that we determined 1,400 millimeter diameter pipe was selected in order to best fit that vertical constraint of that 1.9 meter depth, while maintaining that minimum cover of 300 millimeters for a CL65 highway vehicle loading. The next step, we needed to determine the length of pipe that could meet that stormwater detention storage, basic calculation, volume of the cylinder, and the length of the pipe needed to achieve that 200 cubic meter storage. And then we needed to best fit that system within that 60 meter by 4.8 meter wide footprint, taking into account welds and what have you. So let's look at what we did. So the CSP system here is really simple. So the optimal design here was two main 1,400 millimeter diameter barrels running the full length of the trench, connected by elbows at each end, and two CSP manholes at each end for maintenance as well. So really simple, reduces the amount of fittings, and really maximizes the length of the barrel runs to really optimize that manufacturing process. Some other effective design choices that were taken into account here. They use polymer coated CSP. So using the CSPI Canadian Durability Guideline for CSP culverts, it was determined that polymer coated CSP would provide a service life in excess of 75 years, which was their mandate. The team also chose to use H500 hugger band couplers because of their ability to limit infiltration, as well as their high pull apart resistance. So that also took into account when designing it for that 75-year service life mandate. So the last thing to consider, so there were alternate design choices on this project. There was a precast concrete box culvert solution, but ultimately the contractor decided on CSP for three main reasons. One, the economics, much cheaper, both in terms of labor and material costs. The speed of the installation, it was only needed 10 working days to install the whole system. And three, since CSP is manufactured in Ontario, it's readily available throughout the province. There was a quick turnaround time from engineered drawings to delivery, less than 4 weeks. And, all of these factors combined really produce the best overall solution for everyone involved in the project. So we're able to use a Canadian-made, locally available product to service that stormwater management need, and really meet that design life and that storage requirement as well. And so just to show that these systems really aren't a one-off thing and they're really used ubiquitously throughout Canada, here's an example in Montreal, Quebec of a commercial development project. They also had a small footprint and a very large volume requirement. So their strategy was, this led them to choose a 3,600 millimeter diameter pipe to really maximize that use of that vertical space. So they were allowed by using this 3,600 millimeter pipe to store quite a large amount of volume within a very small footprint. So other options were really considered, but because of this ability for CSP to go up to such large diameters, this was really the best way to reduce footprint, not having to layer any rows of chambers or any sort of other alternatives that may have been also considered. And just a quick picture, they also used access manholes. They had the risers with the ladder access for the maintenance of the systems, and they had multiple inlets and outlets. Just shows the flexibility of CSP to be manufactured in many different ways and incorporate pretty much every part of the system together. Another example in Guelph, Ontario, this is a picture before installation, staging all the CSP within that, that excavation area. During, of course, they used a large diameter as well. They increased that volume requirement by increasing the diameter of the pipe. This was aluminized CSP in this case to, this was appropriate for this site soil condition. But again, large diameter, long main barrel runs allows you for efficient CSP stormwater detention. And, just a quick picture of the parking lot all paved and nice afterwards. It's all hidden underground and you have a nice usable parking lot. Really, instead of using, wet detention pond, you have everything underground and you have a usable parking lot that, has that infrastructure built into it. Again, another example, retail development, Indigo store parking lot, large diameter CSP, long main barrel runs, very few elbows, very few T's. They really want to optimize these systems for the largest amount of volume with the least amount of fittings, and really reduce that footprint and reduce manufacturing time, reduce lead times. Again, same thing, Kitchener, Ontario, another mall, another retail development, reducing that footprint, large diameter CSP, long main barrel runs, good access risers, just built right into that system. Again, out west, same thing. This is a 2,400 millimeter diameter CSP, large diameter, aluminized, long barrel run, very simple installation. As you can see, it's only 2 lengths of pipe, but you can store a lot of volume of water right in those 2 main barrels. Really efficient, quick installation, doesn't really require much heavy equipment, just something to lower that CSP right into that trench, backfill it properly, have connectors, inlets, outlets, header walls. Everything is built in right to that CSP. Really makes for a slick installation that can really be done quite quickly. Okay, So we've looked at some examples. We looked at how to design these things. Let's highlight some of the benefits of CSP used in these stormwater applications and really ubiquitously in many different applications. So we talked about the material coatings, the different gauges, and those are really relevant to the different loads and the different soil conditions that we find in Canada and the different infrastructure projects that we see in Ontario as well. Definitely can be applied to numerous applications, comes in many different diameters, and can be done in custom lengths. CSP is really good at manufacturing that way. You can really, if the project warrants it, you can really design it to have, you know, custom lengths available to you. Transportation savings, you're using many different diameters of CSP on the same project. You can really nest those pipes together and really increases that efficiency of that transportation. Of course, CSP is a flexible pipe and can be installed in many different conditions. We talked about that soil steel interaction. So that's something to really take into account. CSP, when compared to many different options, really is a low cost and very easy to install. Many contractors are very familiar with how to install CSP. Doesn't require much heavy equipment and really can reduce a lot of that labor time associated with that project. And of course, when comparing it to some other products, very lightweight, very environmentally friendly, and steel is a 100% recyclable material. Now, so with that, I'll pass it on to Ray to really dive deeply into that environmental friendly aspect and that recyclability and that sustainable aspect of CSP. So I will mute myself, stop my video.
Thank you, Matthew. Just give me a minute here. Here we are. Okay.
Perfect.
Back in 2018, as an association, we decided to figure out what our carbon footprint was. And by doing that, it's basically a cradle to grave where you go through all of the aspects of producing steel, to shipping it, to manufacturing it and forming it, to shipping it again to a site, and then the end use, whether it ends up in a landfill site or it's recyclable and so forth. And what it's called is an environmental product declaration. So we had this done back in 2018 because we wanted to know where we stood as a material, as an industry. Were we good? Were we bad? How far were we behind the 8 ball? And so the environmental product declaration was produced. It's produced by a third party, which is made up of consultants, climatologists, engineers, environmentalists, and so forth, scientists. And they do a great job of looking at all of the detail from cradle to grave and then coming up with the results of your operation, your material. And then following that, about a year or two after that, we decided we wanted to compare ourselves against other materials, for instance, concrete, which we compete against in the marketplace. How did we compete against concrete? So we had a group Agico out of Montreal do that particular study for us. When you read an environmental product declaration, it's probably about 12 pages, 13 pages, and you can go online and look at, you can find ours at different sites, you can find other materials, and you will find a page in there in one of those 13 pages of the results. And it's not easy to understand at first. It will show the impact category, and then it will show the units of what it's being measured in. It will show the product stage and the end of life. And it will show numbers like, for instance, 5.06 times 10 to the minus 8. Now, I know everyone online here watching will probably be able to compute that very easily, but how many people out of 100 could actually compute that particular formula? Not easy to do. So my hope is that in the future, these environmental product declarations will be much easier to read for everyone. However, I've gone through and I've analyzed this backwards and forwards, And I will show you briefly what the results of 1 metric ton of steel as to what we produce as far as just carbon. I didn't go into all the other details, it's in the report, but our global warming potential would be 1.5 tons of carbon. That's equivalent to driving that automobile 32% of the year, or driving it 5,907 kilometers, heating that home about a quarter of the time, or using 61 propane cylinders for your home barbecue. We have an environmental calculator. It's on our website. It is produced again by a third party, and what it did was look at how CSP compares to reinforced concrete pipe. And if you put in the diameter in millimeters, the length in meters, it will produce what the differences are between the two materials. Right now, corrugated steel pipe has a smaller carbon footprint than concrete pipe. Now, it may change in the future. Both materials are striving towards carbon neutrality sometime in the future. But right now, based upon the public results, that is how they both stack up, one versus the other. And you can change the diameter in millimeters, you can change the length in meters, and it will continue to produce different numbers between the two. We have searched the internet for environmental product declarations for other materials that we compete with, for instance, like high density polyethylene. But at this stage, cannot find any environmental product declarations for other materials other than concrete and corrugated steel. On our website, we have information with regards to the design of underground detention systems for stormwater management. We also have a software. So that's all available on our website, or you can contact me directly at any time if you're looking at finding or looking for some information in this particular area. Just wanted to mention that 100% of corrugated steel pipe is manufactured in Canada. The raw materials that produce those stormwater detention systems that Matthew showed in his presentation are about 80 to 85% Canadian made. There are materials that do come in from the US that are not available in Canada at this point in time, but the majority is manufactured here in Canada. So with that, that is the end of our presentation. Again, I want to thank each and every one of you for attending today, and I'll turn it back to Amin.
Great, and thank you, Matthew, for this presentation. It's very detailed, quite informative. We have quite a few questions. I think we're going to have quite a few more coming up. Let's get on with the first question. Would you, I think this question is for you, Matthew, for the comparison when you're comparing the different products, the larger versus smaller pipe system. Could you also compare the operation and maintenance perspective as well?
Matthew, you're muted at this point. Oh, there you are.
Yeah, so the operation and maintenance for the larger versus smaller will be very, very similar. If there's a CSP system where the diameter wasn't big enough for someone to actually climb down in and maintain it, there are ways of, hydrobacking with a water hose and a vacuum to push whatever sediment that may build up in those systems out to the inlet or outlet control structure, and then vacuum those sediments out as well. Both large and small diameter systems can employ that method of maintenance as well. So they were actually very similar in comparison.
There's another question. What is the expected service life of this system? And how do routine maintenance and major rehabilitation are done? And if I can add, what is the end of life procedures on this? Do you have to rip off, I'm imagining, everything, or can you retrofit? So it's a 3-section question. What is the expected service life, and how is the routine maintenance done?
Okay, so yeah, I kind of touched on the routine maintenance there. Those hydrovac trucks are very useful in that regard. Service life will definitely depend on each project by project basis. The soil conditions and what coatings you're using definitely will change what design service life will be. So for each design, that will have to be specified for each project. And then retrofitting, as Ray was talking about earlier, these systems are very easily retrofitted.
The next question I can see, do you have any advice on design configuration to make future maintenance, such as removal of sediments, easier?
Yeah, so what makes removal of the sediment easier is having that access, that inlet structure right at the inlet, so that you can really guide all that sediment towards the inlet, and having proper manholes along the way to maintain, to monitor that level of sediment within the system, and kind of make sure that everything's above board throughout the operation of that system.
And there's also a number of systems that can clean a lot of what goes in, and capture it, that can be cleaned in some kind of a vault before it even actually gets into the the overall underground stormwater system. So we're not talking about that today, but there are a number of systems that do that. But I think the one thing that the audience should know is that no matter what system is underground, whether it be plastic or concrete or steel, they must be cleaned out. That's a given. I've heard people say at times that certain systems don't need to be maintained or cleaned out. That is very untrue. They all need to be cleaned out from time to time, because even with these cleaning systems that are supposed to capture all of the particles and garbage and so forth that gets into there, sediment still gets down into the underground systems.
Another question on the same topic: how does the cleaning out the system work with the wedges between within the CSP? Wouldn't that be a challenge for having corrugations in the pipe?
I don't believe that would be a challenge. As long as you have the proper equipment to move that sediment out, and I don't see there being an issue with corrugations blocking that sediment movement.
Yeah, plus when you think about it, the corrugation, there is a corrugation. It's not smooth wall. It can be smooth wall if that's what they want, but there is a corrugation. But even so, they're pretty small when you think about it. So when a vacuum gets in there, they can pretty well suck everything out of there.
Mm-hmm. Another question came in, what are the welding requirements for the CSP joints? Is there a standard that that you can refer them to?
It is geez, I didn't expect this question, but it's CSA, and you might catch me here, but I believe it's CSA W59. I'll tell you what, ask Matthew another question. I'll look it up right now in the standard. Okay.
Okay. Yeah. Now there's another question. It's quite a long one. Underground systems allow for development, including hard surfacing over top of the system, which is great for smaller considered sites. That's the attendee's opinion. But also increases the post-development runoff from the site. On larger systems, would you still recommend the use of underground CSP systems?
That's probably where I would recommend the use of CSP systems the most in these large systems. As long as you have the proper depth of burial, you can really get an efficient use of that volume using CSP. So yes, I would recommend for large systems specifically, actually.
And then just to go back to that welding question, we use two standards. One is W47, which is the certification of companies for fusion welding of steel. And the other one was the W59 that I mentioned, which covers the welded steel construction or metal arc welding. So those two standards our members follow with regards to this particular area.
Thank you, Ray.
Okay.
I don't see any other questions coming up. Perhaps we might see some in a bit. I have a question in my mind from a municipal perspective, because usually these projects would be part of a development, and the municipality would assume responsibility of the whole system afterwards. So do you have existing systems that reached or close to their end of life, so that you can give a perspective of what the municipality would expect I don't know, 50 or 70 or however the end of life period is, what significant replacement or end of life procedure should they expect?
I'm not sure how to answer this. I mean, I don't know of any systems that are in that category that you just mentioned at this point, as far as, I mean, I go back to the 1980s, and a lot of the stormwater management systems or detention type systems that were installed in the 80s and the 90s are still functioning today and are still being routinely maintained. I would assume that, you know, if there were any issues with regards to, you know, maybe some issues with the inverts, if there was any corrosion that took place or whatnot, you know, they can be rehabilitated without taking down the whole structure and redoing it, if that makes sense. So I can't, even from experience, I can't tell you of any systems that I have seen that have been, say, ripped up or, you know, major rehabilitation has taken place at this point in time. I had a question the other day from a consultant who was looking at a pipe in a stormwater pipe in Thorold, Ontario, that was installed in 1965, which is what, 60 some odd years ago, give or take. And he was, he sent me pictures and everything looked absolutely fine. His questions were more on what coating was used back then, what kind of corrugation profiles are there. They had to have divers actually go down and look at this system. So, you know, I guess that's all I can add at this point, unless Matthew, you have anything to add on that.
I was going to say, in my experience, which is, you know, way less than your time span of experience, I haven't seen anything ripped up or, you know, replaced. So I'm glad you said the same thing, because yeah, that's pretty much it.
I appreciate that. I appreciate the answer. I have another question. How does the cost of this system compare with alternative systems that are out there?
Typically quite cost effective. If you consider the local inventory of CSP within Ontario, low freight costs, and of course, low turnover time, which really, you know, shortens the life, that operation period of your project. That full scale cost reduction really is significant when comparing to these other systems as well.
Yeah, CSP does very well with regards to minimal height of cover compared to some of the other systems.
Yeah.
See, a question came up asking, any example of combination of CSP detention tanks and LID?
I'm kind of confused by the questions of low impact development, really the general term for, you know, restoring that natural hydrology of the site to its pre-development stage. So yes, a CSP detention tank would help in that as well, if that was part of the stormwater management design, right? So yeah, CSP is one of the tools that you would use in an LID.
Also, another question asking, what are the design considerations for construction beneath buildings and material sorting areas, if that's possible?
So generally detention systems are designed to be under some sort of flexible pavement or rigid pavement. And, we really prefer not to install them under buildings. So if a system is to be built under a building or, all those live loads and dead loads really need to be accounted for. So it may increase the gauge or the backfill material of the system. But special attention really needs to be given to that zone of influence of the foundation of the building. And then access for maintenance as well must be addressed. So those projects really need to be evaluated on a project by project basis, but in general, we really don't recommend putting the system underneath the building.
Another question asking, can you use the CSP detention system in high water table environments?
So it's simply, yes, we can. So the detention systems definitely can use in high water table environments. The use of like tie downs or special backfill may be recommended to counteract buoyancy issues. You just have to do those calculations for that uplift force and what the weight is to counteract that uplift.
Thank you. Another question just came in. Have you thought of developing SWM detention system featuring CSP and HDPE channels of square rectangular cross sections that would provide significantly larger storage?
Can you just repeat the question again?
They're just seeing if that's a possibility. Would you consider or had the thought of developing SWM stormwater management detention system featuring CSP and HDPE channels of square or rectangular cross sections to provide larger storage?
That's not something I've really come across. Using both materials in the same system is what they're referring to. I think. I mean, I guess it's possible, but if CSP was appropriate for the installation, I guess you'd have to compare the cost versus the diameter of those pipes and how high, how high of a diameter can HDPE go up to. So I guess it would just depend on the project, depend on the diameter of the pipes.
With the corrugated steel pipe, would you be able to make it into a square or rectangular cross section?
No, you won't have a square CSP pipe, and you wouldn't have an HDPE square pipe either. I'm not sure exactly what they're referring to for square rectangular cross section. Maybe that full envelope of the backfill with the pipe inside. If that's what they're referring to, but
the pipe can be arched, but not square.
All right. I don't see any more questions coming up. One more came in. Person is asking, you mentioned about 300 millimeter minimum coverage on CSP storage system. How would you manage the stored water in freezing season?
Those freeze thaw cycles are pretty ubiquitous across Canada. So those standard development for minimum covers have been in operation across all different areas within Canada that have that same freeze thaw cycle. So I don't think that would be an issue for cracking or heaving during that freeze thaw.
Thank you. All right, I don't see any other questions coming in. Math or Ray, do you have any final comments or anything that you want to mention?
I would like to say that for all of you who have attended today, there will be a certificate sent to you, your email, giving you 1 hour of professional development. I want to thank each and every one of you for attending If you need any information in this particular area, you can either email myself or Matthew directly. You can go to our website at www.cspi.ca, and all of the information is on our website. And if you have any trouble ever finding anything, please just reach out. We're an email or a phone call away. So thank you.
You're right. All right, for that, we'll gladly end this today's webinar. It was a great chance learning about the systems for stormwater management from you, Matthew. And thank you, Ray, for always bringing in these opportunities for learning. Thank you both for your time. And thank you to everyone that attended today.